Hello and welcome to our next video topic in chemistry. Our topic is quantum mechanical model part 2. So just to clarify, if you have not yet watched the video notes of quantum mechanical model part 1, stop this video right now, go back and watch it. Otherwise, there will be some things in this video that don't quite make sense. So if you are watching this video on the day it was assigned, fill in your date. We're in Unit 7, Day 3. If you're watching this video for any other time, welcome. I'm excited to explain some chemistry things to whoever is listening. The essential question we're going to answer in today's video notes is, how does the quantum mechanical model describe the location of the electrons? So this video notes is assuming you already kind of know the different parts of the quantum mechanical model, things like energy levels, sublevels, orbitals, that kind of stuff. But then this video lecture will explain, well, how do we actually locate the electrons using that quantum mechanical model? All right, finish setting up your focus notes. When you're ready, let's get into it. All right, so we're going to learn something called electron configurations. That's the thing that will answer the EQ for today. So an electron configuration describes how are those electrons specifically arranged around the nucleus. It's like the address of each electron. So again, if I wanted to mail you a birthday card, instead of just saying, oh, send it to Minnesota, because I know you happen to live in Minnesota, it's probably not going to get to you. You have to be more specific. So just like you can't say, now that you know more chemistry, you can't just say the electrons are in the electron cloud. It's not specific enough. We need to know, well, what energy level are they in? What sublevel are they in? How many electrons are in that sublevel, so that we understand, again, this will help us understand about light and energy and bonding and why some elements are considered stable and not. All of that is wrapped into this idea of electron configurations. So even though this is a super, super specific topic in chemistry, it helps us understand a lot of big ideas. So I get excited about this to help you understand more about the electrons around the nucleus. All right, here's how it works. There's 3 rules that kind of help us write an electron configuration. The first one is something called the Aufbau Principle, which is a German word that means building up. So what that means is the electrons enter the lowest energy orbital first. So what is the lowest available energy level and sublevel, and then the orbitals are in those sublevels, it fills those first. It doesn't just randomly fill up wherever it can. It starts with the lowest and goes up. So like the idea here is, if this is my nucleus, I want to fill my first energy level. When that's filled, then I go to the second energy level. When I go to the third, I go to the next energy level, and it continues on from there. So whatever is the lowest energy orbital gets filled first, and then we go on. The next rule is called the Pauli exclusion principle. Remember how we said that orbitals can hold up to 2 electrons? But remember, electrons are negative. So if I have 2 negative electrons sharing an orbital, wouldn't we think they try to repel away from each other because they're both negative? Well, that's taken care of by the Pauli exclusion principle. So the idea here is that you've got a nucleus and you have electrons that are going around that nucleus. But look at, the electron is also spinning as it goes around the nucleus. It's very much like what our Earth does. Our Earth spins on its axis as it rotates around the sun. It's the same thing with electrons. They are spinning in their own axis while they orbit the nucleus. And what Pauli exclusion principle says is, if 2 electrons are in the same orbital, they have to be spinning in opposite directions. So if this electron was spinning counterclockwise, so spinning to the left, if there's another orbital or another electron in its orbital, it would need to be spinning to the right. Otherwise, their negative charges would repel them out of the electron cloud. So opposite spin. So again, think counterclockwise and clockwise as they rotate around the nucleus. The way we show that in the chemistry world would be up and down arrows. So here's an energy level 1, sublevel S, 1 orbital, 2 electrons in opposite spins. Here's energy level 2, sublevel S, 1 orbital, 2 up arrows, nope, not allowed, because they would repel themselves out of the electron cloud. Opposite charges, up and down arrows to show opposite spins. And then this is an element that must have 1, 2, 3, 4 electrons. There's the 2p sublevel that has 1, 2, 3 orbitals, but there's nothing in those orbitals because you fill the lowest energy orbitals first. So it's not like I put 1 here and then 2 there and then maybe a 4th one over here. Nope, because you have to fill the lowest energy orbitals first. But then if you have to share an orbital, they have to be an opposite spin. Aufbau, Pauli exclusion. Okay, third rule, Hund's rule. All right, so remember that picture I just showed you that showed there was 3 orbitals in 2p? If you had 3 electrons in the 2p, 1 electron enters each orbital until all the orbitals have 1 electron, and they only double up if they have to. Here's my analogy. Imagine that you had a soccer game, and the soccer game didn't go very well. There was lots of mistakes. There was some fouls and, like yellow cards. You lost the game. It was not a great game. Plus, the day before, it had rained really hard, so the field was just a disaster. Mud and it's dirty, and you're not happy, and whatever. So when your team gets on the bus, it's like, there's a bunch of negative energy, right? Like no one's in a really great mood. You're tired, you're hungry, you're muddy. Everybody sits in their own seat on the bus, and you only double up if you have to, because you don't want all that negative energy next to each other. You just want to be by yourself. That is the analogy of Hund's rule. If the electrons can take their own seat orbital, they take their own seat and they only double up if they have to. Here's a chemistry example. Imagine I had a 3D sublevel. So it's the third energy level, D sublevel. D sublevels can hold 1, 2, 3, 4, 5 orbitals, and that would be a total of 10 electrons. But if I only had 5 electrons, that means I can put 1 electron there, 1 electron there, third electron there, fourth electron there, fifth electron there. And this is that up versus up and down spin, a one-sided arrow to represent an electron. That's a notation that chemists use. So if I have 5 electrons and 5 orbitals, they can each take their own seat. But remember, each orbital could hold 2. So that's why someone might say, well, wait, why don't I just put 2 of them there, 2 of them there, 1 of them there? Having empty orbitals is unstable. It would rather have it all spread out, evenly spread out, in that instead of having 2 and 2 and 1 in each of the orbitals is more stable. Think of it as just like spreading out that negative charge evenly. It makes that electron cloud more stable. And remember, in chemistry, in the natural world, everything tries to be as stable as possible. So that's Hund's rule. So if the electrons can take their own orbital, they will, but they have to fill up an orbital sublevel before they go on to the next sublevel. So it's not like everyone can just take their own orbital everywhere in the electron cloud, just within the same energy sublevel. All right, why don't you go ahead and do a level 1 question so far? So think about those 3 rules. Think about the definition of electron configuration. Go ahead and write a level 1 question, pause, kind of think through those notes so far, get caught up, come back when you're ready. All right, so now let's talk about actually writing an electron configuration. So this is an energy diagram, and you can see, okay, so yellow seems to be the first level, and then there's a 2s and a 2p, and then a 3s and a 3p. But then notice it looks like 4s is actually less energy than 3d. Okay, well, maybe that makes sense because it's just 1 orbital, and then this is 5 orbitals, so that takes more energy. But then 4 is a bigger sublevel, and so it just starts to get kind of complicated when the electron cloud gets farther from the nucleus. It's really just a pattern. So this is an energy diagram. Sure, it's great, little circles and labels and stuff. The Aufbau diagram, we can actually draw it. So draw this with me. The Aufbau diagram is showing us the order that the electrons fill the electron cloud. We start with our first energy level, and remember there's 7 energy levels total, but we start at the bottom with 1 because that's the lowest energy nearest the nucleus, and then it goes up to 7. So start by going 1 up to 7 and make this really organized with even like rows and columns. Remember in part 1, we talked about the fact that the energy level tells you how many sublevels there are up to 4. So energy level 1 has 1 sublevel and it's an S. Energy level 2 has 2 sublevels and it's an S and a P. Because remember, there's always starts with S and then it's SPDF. Energy level 3 has 3 sublevels, S, P, and D. Energy level 4 has 4 sublevels, S, P, D, and F. But remember, that's the maximum number of sublevels. So 5 is also S, P, D, and F. 6 is S, P, D, and F. 7, S, P, D, and F. Okay, get caught up on that so far. Pause the video if you need to. But then here's the thing. Sometimes it's not just as simple, it's just not as simple as all the ones, all the twos, all the threes, all the fours. It doesn't feel like that because, for example, a 4s is not as complicated as a 3d is because d has 5 orbitals in this sublevel, which is 10 electrons. And S is 1 orbital, 2 electrons. So it's easier. So even though the 4 is a little bit bigger, the 3D has way more electrons to deal with. So it goes in this pattern, so that's the pattern we're learning, by diagonal. So first, 1s. So go ahead and draw an arrow, diagonal. After 1s, then comes 2s. So then I got my next diagonal. After 2s goes 2p. Next diagonal, up to 3s, because now there's more things to point to. After 3s, now we're going to go to the bottom here. We're going to go from 3p to 4s. And then we're going to look at what's next diagonally. What's next? Yeah, 3d. But then it'll be 3d, 4p, 5s. Okay, now what would come next? What's not crossed off? Yeah, 4d up to 5p, 6s. Do you see it? Okay, what would come next? What would be the next thing to kind of cross off? Do you see it? Yeah, 4f. But then that will go from 4f to 5d to 6p to 7s. And then that pattern just keeps continuing. Now, it turns out that we don't have enough electrons to fill all the way to a 7f because you would have had to fill up everything else before it. That's Aufbau Principle, right? So you have to fill up everything. So if you add up the number of electrons on the periodic table, the maximum we have is 118, and this is way more than 118. But if we create more elements, which would have more electrons, then we would have to get up to this. But maybe we create another energy level of 8. Oh, there's so many other things that might need to happen. But this is the pattern for the electrons and elements we have now. Let's do a couple examples together. So how do I use this to actually write an electron configuration? So a couple examples. Let's start with silicon. Well, if I'm writing an electron configuration, I have to know how many electrons there are. So I find silicon, here it is, electrons. In neutral silicon, that's what this is, just normal element silicon. Remember that the atomic number is the number of protons, which are positive, but the electrons have to match the positive protons. So the 14 is also the number of electrons for neutral silicon. So this was my pattern, right? So I'm going to start with my 1s, so 14 electrons. We'll start with 1s, okay? So the first thing we would write down is 1s. S has 1 orbital, and it can fit 2 electrons. So it looks like this, 1s2. And be picky the way you write it, not for Killinan, but for chemistry. It has to be a big number 1, small lowercase s, and a superscript 2. Energy level, sublevel, how many electrons? And then you don't put anything in between, but we go next. After 1s, start at the bottom of the arrow, we go to 2s, okay? Energy level, sublevel, 2 electrons. I have 14 electrons total, 1, 2, 3, 4, so I keep going. After 2s, go to the bottom of the arrow, 2p. But remember, p's have 3 orbitals, 6 electrons, 2p6. So 6, 7, 8, 9, 10. I have 14 electrons, I have to keep going. So after 2p6, follow the arrow, comes 3s, s1, once the s sublevel has 1 orbital, which can hold 2 electrons, so 3s2, and now that's 12 electrons, meaning I have 2 left. So after 3s, go to the bottom of the arrow, comes 3p. Now, the p sublevel has 3 orbitals, but I only have 2 electrons left, so it would just be 3p2. So again, be picky the way you write this because this is how chemists around the world do this. Big number for energy level, lowercase sublevel, and then up above is how many electrons in that sublevel. Now, the reason this is interesting for chemistry is it tells us I can look at this and I can say, wait, I know that silicon's not stable. How do I know? Because it's got an open orbital, because P has 3 orbitals and there's only 2 electrons in there. So there'd be 1 electron in the first orbital, a second electron in the second orbital, and an open third orbital. That is not preferred in the chemistry world, having open spots. And so that tells me something about silicon. It would probably want to get rid of these 2 electrons and then it would have a full 3s, and that's considered more stable. So that's kind of the idea of what we use this for. The other thing that's useful is that we can start predicting what this element might do in terms of electrons moving around. So what levels might it go to? How many electrons can move around for silicon? So light, energy, bonding, stability, that's the purpose of the electron configuration. Let's do another one. How about cesium? All right, so find cesium. Oh, here it is. Cesium is element number 55. 55 protons that are positive means there has to be 55 electrons that are negative to balance it to make a neutral cesium atom, which is what this symbol is showing, no plus or minus charge. All right, start at the bottom. Aufbau Principle says always fill at the bottom first, and then we keep going in this pattern at the bottom of the arrow. So first we go with 1s. S has 1 orbital, 2 electrons, so 1s2. Then we go to the bottom of the arrow, 2s. S's still can only hold 2 electrons. Bottom of the arrow now 2p. But remember, p's have 3 orbitals, so it can hold 6 electrons. After 3p goes 3s back to just 2 electrons because s's sublevels only have 1 orbital, maxes out at 2 electrons. After 3s, go to the back to the bottom of the arrow, 3p, back to 6 electrons because p's hold up to 6 electrons because they have 3 orbitals. All right, after 3p, follow the arrow, 4s. We're back to s's, so that's 2 electrons. After 4s now, go back to the bottom, 3d. All right, we haven't done a d yet. All right, well, d's have 5 orbitals, which means 10 electrons can fit. We're spreading out 55 electrons. Let's make sure we're not past that yet. 2 and 2 is 4, 10, 11, 12, 18, 19, 20, 30. All right, so I'm at 30 of my 55, and I just filled up the 3d. 3d is filled. Now go to 4p. P's have 3 orbitals, 6 electrons. And then after 4p comes 5s, but that's only 2 electrons. All right, let's keep going. After 5s, I go back to the bottom of my arrow, 4d. But remember, d's 5 orbitals, 10 electrons. So I'm starting to fill up my electron cloud. Let's double check. So this is 4, 10, 11, 12, 18, 19, 20, 36, 37, 38, 48. All right, so of my 55, I'm at 48 electrons. All right, so I just filled 4D. So back to my guide here, 4D. Next would be 5P, but P's have 3 orbitals, so 6 electrons. I'm at 5P, so next would come 6S. But we had 7 electrons. Remember, we were at 48, so now I'm at 54. So then I only have 1 electron left. So even though that 6s could hold 2 electrons, I only have 1 electron left. So that tells me cesium is not stable. It's got half an open s sublevel, and that's not preferred. So instead, it would like to get rid of this sublevel, because then look at the 5 would be filled. The s would be filled, the p would be filled, the d is filled beneath it, so that's way more stable. Well, we've kind of talked about that before. Look at where cesium is. If it loses an electron, look at it's in the noble gas column, and we say that's stable. Now we're starting to get at why it's stable, okay? So let's just double check our math. 55 electrons is what we should be showing. 2 and 2 is 4, plus 6 is 10, plus 2 is 12, 18, 19, 20, 36, 37, 38, 48, 54, 55, okay? That is how you write electron configurations for any element on the periodic table. You start with 1s2 and you go all the way up to however many electrons there are, okay? So let me make a connection between that periodic table and electron configurations. It's a way to do a really fast check your work. It turns out that the reason the periodic table is shaped the way it is because of the 4 different sublevels, S, P, D, and F. So the S block is the first 2 columns because there's a 1S and a 2S, or a 1S1 and, S1 and S2. The 1 or 2 or 3 depends on what row you're in. But you could always have an S1, you could always have an S2. The P block, look at this. Think about it. How many electrons can fit in the P block? Oh yeah, 6. How many spots over do you think the P block is? 1, 2, 3, 4, 5, 6. It matches. The D block, so it's this big section here in the middle, without even counting how many across do you think the D block is? Well, D sublevel has 5 orbitals, 10 electrons. It is. It's 10 across. That means the F block way down here must be how many across? 14. Yep, because the F sublevel has 7 orbitals, which can hold 14 electrons. So here's how we can use this to check our work. So remember when we did silicon, it was right here. If you look back at the answer you gave for silicon, it was 1s2, 2s2, 2p6, 3s2, and then 3p2. So the end of your electron configuration shows you where it is on the periodic table. So in this case, it was the third row, the second p block. So third row, 1, 2, second p block, it is. Let's check it for cesium. So cesium was right here, which means that it should end in 6s1 because it's in the sixth row, the S first column of the S block. And it was. If you look back at what we wrote out, 6s1. So the last part of the electron configuration matches the location on the periodic table. So whatever element ended in 3d3 would be this element. Whatever element ended in 7p2 would be this element. And then that pattern continues. All right, so eventually when you get to know your periodic table better, instead of using that arrow diagram with all of that thing that we drew, you'll be able to write electron configurations just by looking at the periodic table. But that's getting just a little bit ahead of ourselves. Go ahead and do a level 2 question. A great level 2 question, pick any element and say, write the electron configuration for this element. Pick one. That's a great level 2. All right, let's finish up today's notes. So it turns out that actually there are 4 quantum numbers to fully describe one electron's position in the electron cloud, like its address. So we've already talked about 2 of them, and those are the 2 that we talk about in pre-AP Chem. The principal quantum number, which could be 1, 2, 3, 4, 5, 6, 7. The symbol is N. We've also talked about the angular momentum quantum number, which we called sublevel, which could be either S, P, D, or F. The symbol is an L, and it's either 0, 1, 2, or 3. So the L value is 0, L value is 1, 2, and 3. And it turns out, though, if you want to know the full story, you'd have to know the orientation in space, which axis is it on, and remember how we said they're spinning? You would need to know, is it spinning counterclockwise or clockwise in space, on the sublevel, in the energy level where it's located. So we, again, in pre-AP Chem, we're just talking about principal quantum number, which is energy level, and sublevel. If you want to know more, that's my advertisement to sign up for AP Chem, and then you'll know even more about the electron cloud, more than you even knew there was to know, and that is the fun part about chemistry. All right. Related to today's notes, there are 2 elements on the periodic table, just 2 of 118, that we have found out, we being scientists in general, that don't follow the pattern of the Aufbau diagram. Only 2. But I want you to read about them instead of me just telling you, and I want you to see why they are exceptions. It has to do with stability. So open the reading from Schoology, put it into Notability, read it before you do the practice assignment, because I'm just going to tell you, spoiler alert, the 2 exceptions are on the assignment. So if you don't do the reading, you're going to for sure get those 2 wrong, okay? The worksheet is due Tuesday. If you're watching this on the day it was assigned, and so you need to read the reading before you do the worksheet. Otherwise, you'll for sure get 2 of them wrong. And that brings us to the end of our notes for today. Write your level 3 questions. So again, thinking about, why might I need to do this, or predict a situation where knowing the electron configuration is useful, that kind of stuff. And then write your summary. Don't forget to do them, because remember, the purpose of those things, the cluster questions and the summary, they help you process the notes. Instead of just writing down the notes and being like, well, I'm done, you got to process to see if things made sense, to see if you understood them. Writing the questions and summary is a way for you to check for understanding. That brings us to the end of part 2. So if you're doing this watching this video when it was assigned in class, the things you would also be working on are anything from week 1 of the trimester, the flame test lab report, full lab report, the quantum mechanical model part 1 and 2, Costa questions and summaries. And then you're going to do that reading about exceptional electron configurations. You're going to start the electron configuration sheet, but the next class day, you'll have time to ask questions. So don't worry about finishing it right now. Just start it, because it processes, can you write electron configurations kind of on your own? There are also some unit practice problems that go with these notes. So parts 1 and part 2, put them in the back of your notebook, check your answers. It's a way to do immediate feedback to see if these notes are making sense. And then just a plug as if you need some extra help, just because there's lots of details to process here. So if you need some help, come to my office hours, Monday through Thursday from 2:15 to 3:15, or Friday from 1:30 to 3. Thanks so much for your attention today and learning even more details about that amazing electron cloud. See you next time.